Hi, everybody. Thanks for joining us tonight. We have Michelle Nichols with us from the Adler Planetarium for Through the Eyes of Hubble. So Michelle is the Director of Public Observing at the Adler Planetarium in Chicago, Illinois, and has worked at the Adler since June 1995. She holds a Bachelor of Science degree in Physics and Astronomy from the University of Illinois at Urbana-Champaign and a Master of Education degree in Curriculum and Instruction from National Louis University. Ms. Nichols leads all of the Adler Planetarium's telescope, observatory, and public sky observing initiatives and events. This is her third event with us tonight, and unfortunately our final, but we really appreciate her time and expertise. Just as a little plug, her first two programs are available on our YouTube site, so you can go to youtube.com/Kenosha Public Library to see those as well. And I'm going to let Michelle go ahead and get started.
All right, thank you so much. Hi, everybody. Thanks for coming, and hope everyone is having a good week so far. And this talk, Through the Eyes of Hubble, is the talk that I've been doing the longest. I've been giving talks for libraries for over 20 years. And some form of this presentation has been on my roster the entire time. And I don't think I would have imagined that I would be doing this talk for as long as I have been, because the telescope has lasted that long. But also because people are still interested in it. And the telescope has been in space for over 31 years. And that is remarkable. There are very, very few spacecraft that last that long, especially one that gets used as much as this one does. So what we're going to talk about is a little bit about the history of the telescope. Then the majority of the talk will be what are some of the major things that the telescope has been most remarkable at. So how it has influenced astronomy and in what ways. And yes, there will be lots of pretty pictures. So I hope you can sit back and relax and enjoy those. And then finally, at the very end, I'll have a little bit of information about the successor to the Hubble Space Telescope, which is the James Webb Space Telescope. And that is scheduled to launch a week from Wednesday, I believe, December 22nd at 6:20 in the morning. And I know the library is planning a launch party for that. So fingers crossed it does not get further delayed, but we're getting down to the wire here. So the only thing at this point that could probably delay it would be weather, weather or a mechanical problem with the rocket. So again, fingers crossed that it happens. All right, so I'm going to share my screen. So give me just a second while I get that arranged here. All right. Okay. So telescopes in space have been dreamed of since 1946, probably even before then. But in 1946, there was a scientist by the name of Dr. Lyman Spitzer. And he wrote a paper about the benefits of putting a telescope into space. The major benefit for that is to get above the blurring effects of Earth's atmosphere. You're looking through a sea of air. And even though at night the air is clear, for the most part, it's still, the air is at different temperatures, and the view kind of jiggles around a little bit. You've got the air at different temperatures causes the light from whatever you're looking at to jiggle, to wiggle a little. And so we call that twinkling, or scintillation is the science word for it. And so if you get above the air, you can get above that twinkling effect. And so you don't need a huge telescope in space. You just need a good one. And so, but note, 1946 was 12 years before we started putting anything into space. We started thinking about a large space telescope in the early 1960s. the program was approved and the telescope was started to be built in the 1970s. And here is a drawing of essentially what the telescope ended up looking like. So you've got solar panels for power. You've got instruments at the back. The light comes in from the front and it reflects off of the main mirror and throughout the telescope here. And then finally, it goes to those instruments in the back there. We've got some antennas for communicating with Earth. And this is essentially what the telescope ended up looking like. Now, the building of it was happening in the 1970s, and this was at the same time that the space shuttle was designed and built. The two grew up together. The Hubble Space Telescope was designed to be launched by the space shuttle. The Hubble Space Telescope was designed to be serviced by astronauts aboard the space shuttle. So even when they put it into space, they could periodically go back to it, retrieve it, do some work on it while it was in space, switch instruments, fix things, whatever had gone wrong. And so it could be a very versatile telescope. So you could improve the telescope over time by putting new instruments on it. What you're seeing here is a very early image of astronauts training to service the telescope. And so a very rudimentary setup for the telescope. This gives you a sense of the size of part of it. So kind of big, but next time you take a look at a school bus, that's about the size of the telescope itself. So it is not the largest telescope by far. There are a lot of telescopes on the ground now that are much bigger than the Hubble Space Telescope. But the reason it is so good, two reasons. Number one, it's above the air. And number two, astronauts were able to service it from time to time. That will play a part in our story in just a little bit. The telescope uses a mirror, a curved mirror, to collect light from distant objects. The telescope orbits Earth and it looks at faraway things. The mirror was built and shaped here on the ground. It's made of glass, and you can see the main shape of the mirror. This is the mirror that eventually went into the telescope. It doesn't look like a mirror because it doesn't yet have its reflective coating on it. But take a look. This allows you to see the back of the mirror. It has a honeycomb structure, so it's not one solid piece of glass. There are a lot of openings in the back to reduce the weight. So essentially to hold the shape, but reduce the weight. If this were one solid piece of glass, it would have weighed 8,000 pounds. But because they were able to take chunks of the glass out from the back, they reduced the weight to about 1,800 pounds. What does that do? It allows you to have less weight overall for the telescope. Every ounce you have to send into space costs a lot of money. And so any chance you have to reduce the weight of the telescope is good indeed. Now, the telescope itself was pretty much at the limit approximately as to what the space shuttle could carry safely. So again, very good reason for reducing the weight of this thing. What you're seeing these folks do in this picture is analyze the shape of the mirror. That will also play a part in our story in just a second, but the shape of the mirror is essentially shaped like a very flat bowl. So if you have a shaving mirror at home, that gives you a sense of the shape of the telescope mirror. So next time you take a look at a shaving mirror, feel it. You might feel a slight bowl shape to that mirror. Construction of the telescope happened between the 70s and early 80s. It was completed in 1985 and it was tested and ready for launch. It was supposed to launch in 1986, but unfortunately the Challenger space shuttle disaster happened. And so that grounded all space shuttle flights for 2.5 years. By the time the space shuttle was launching again, it was September of 1988. And so that basically put a big backlog of all space shuttle launches. And so the telescope was supposed to launch in 86. It launched in April of 1990. And this was aboard the Space Shuttle Discovery. And this is a picture of the launch right here. So The next day, so this is April 24th, 1990, the next day, they took the robotic arm of the space shuttle and grappled onto to essentially a holder on the side of the telescope, lifted it up out of the payload bay of the space shuttle, and let go. Because the space shuttle was traveling at orbital speed, 17,500 miles an hour, the telescope was traveling at 17,500 miles an hour. It orbits about 350 miles up, and you don't need rockets to keep you in orbit. Once you're going at orbital speed, unless something else slows you down, you're going to keep going at orbital speed. So the telescope is up there. Again, it orbits Earth, not too far away. And so next time you get a map out, find some place that's 350 miles distant. Figure out what that is. Now imagine, instead of going along planet Earth for 350 miles, you go up 350 miles. So just to give you a sense of scale here. There was a problem noted right away with the telescope when they started taking images at all. What they saw was very concerning. So what you're looking at here is a picture of a star. It should be a picture of a pinpoint perfect star. You're not seeing that. You're seeing a bunch of, looks like halos and other strange shapes around the picture of the star in the middle. And what this meant to the engineers, the scientists right away, was there was a huge problem with the telescope. The shape of the mirror was incorrect. The bowl shape of the mirror essentially had a lip to it. The edge of the telescope mirror was ground slightly too flat. How slightly too flat? Well, take a human hair, divide it into 50 pieces, and that 1/50th of the thickness of a human hair, that's how little wrong the telescope mirror actually was, but it was enough. It meant that not all of the light from whatever it is they were looking at was being concentrated correctly. The story that got out to the media, what they ran with was, oh, the telescope's broken. Not so fast. Here we've got a picture of Pluto and its moon, Charon, its largest moon. Charon is about half the size of Pluto. This picture on the left was the best picture we could get of the two at the time. You can almost not tell that Charon and Pluto are two separate objects. The picture on the right is the picture of the two with the flawed mirror of the Hubble Space Telescope. Even with the flaw, the image was better than anything we had on the ground. But again, unfortunately, everyone was kind of running with, oh, the telescope is broken, can't use it for anything. Not really. As long as they could adjust for the shape of the mirror somehow, then that would make the telescope back to what how it's supposed to work. So that's what they did. In about 3 years since they launched the telescope to December of 1993, they figured out what the shape of the mirror really was. They looked at a lot of stuff and went, okay, well, all right, we understand the shape and the flaw really well. Let's build eyeglasses for Hubble. And that's what they did. So on the first servicing mission, which was December of 93, they changed out the main camera of Hubble. So this is the new camera. And this camera had the optics built into it to adjust for the flawed mirror. Then there are some other instruments that are on the telescope, and they needed to have something essentially be eyeglasses for those instruments as well. And so that was called CoStar. And it stands for something, and I don't remember what it stands for, but that's okay, because CoStar essentially was eyeglasses for all the other instruments. What you have then is a telescope with the flawed mirror still in it. It's been in it this entire time. They didn't change out the bad mirror and put a new one in. You saw how big of a mirror that was. It would have been too bulky, too heavy, and they just didn't have a way of changing the mirror itself, but they could change the cameras and the instruments. And so once they did that, well, here's an example of what it did. The picture on the left is a picture of an astronomical object called a galaxy. And Honestly, it doesn't matter what it is. Take a look at the picture on the left. Does it look different from the picture in the middle? The picture in the middle looks sharper. You can see more detail. So yeah, without even knowing what this is, which again, that doesn't matter, you can see that there was vast improvement in the quality of the pictures. The picture on the right was looking at the same object in 2018. They had replaced the camera again on the final servicing mission, which was right around the year 2010. The telescope is better now than it was when it launched, even better than when it was serviced the first time. And so the telescope, some people say, is the most influential telescope in history. That's saying a lot. There have been a lot of really influential telescopes. But I'll give you one example as to how it's influential. You've heard of it. Name the name of two other telescopes. A lot of people would have a really hard time even naming the name of one other telescope that's operating on the ground or in space. And so you've heard of this thing. You've seen pictures from it. You may not even have realized you've seen Hubble Space Telescope pictures, but it has really changed astronomy fundamentally. So I'm going to show you some examples of how astronomy has been changed for the better because of the Hubble Space Telescope. All right. We can use the telescope to keep an eye on the neighbors. What I mean by that is not that Hubble is reading your newspaper over your shoulder when you walk outside in the summertime and read a magazine or something outside. Hubble is not looking at Earth. It is not a spy satellite. Hubble looks at far away, dim, distant objects. But we also can use the telescope to look at objects in our own solar system. So some of the stuff nearby, planets, moons, asteroids, comets. How about this picture of the planet Jupiter? This picture was taken in 2020, so last year. You can see the amazing detail of this telescope. This object right here, which you can also see detail on, you can see some shading differences. That is Jupiter's moon, Europa. This is part of a yearly series of images that they take of Jupiter, Saturn, Uranus, and Neptune. The reason for that is we don't have spacecraft, or we haven't had spacecraft at those planets the whole time Hubble has been flying. So there is a spacecraft at Jupiter right now. It's called Juno. But we haven't had one there the whole time. So still, we take pictures using Hubble of Jupiter, Saturn as well. And storms pop into view and disappear. The shapes of storms change, the cloud bands change, the colors change. Here's an example. This picture was taken in 2020. This one was taken in 2018. I can just toggle back and forth between the two. Again, you don't even have to know what's going on with these two pictures. You can tell the difference between these two. Colors are different. You can see more or fewer cloud bands depending on the picture. You can see that the haze near the North Pole of Saturn is kind of red. The haze at the South Pole is kind of blue. Northern hemisphere of Saturn is experiencing summertime. The southern hemisphere of Saturn was experiencing wintertime. And so this is a really interesting way to keep track of what's going on with these planets. Uranus and Neptune have only ever been visited once by a spacecraft, and that was Voyager 2 in the 1980s. And we haven't had anything go out there since that time. So it is a really great way to use the same instrument over and over and over to go back and look at these objects. And that's actually very important for science. Repeatability. Use the same telescope, the same instrument, the same camera or a similar camera to be able to take those pictures year after year. So this has been really amazing that we've had this telescope around for this long. Even when a spacecraft flies past a planet, it may not see everything. This is a picture, or actually it's two pictures taken by Hubble of the planet Neptune. And the reason there's two separate pictures, Neptune is the planet, it has rings. Neptune's rings are very dim. The rings are separate from the planet, but they're very dim. In order to photograph the rings, you would end up overexposing the planet in the picture. To take a picture of the planet, you don't have the camera open long enough to get the rings. So you have to take two separate pictures and then combine them in order to get both in the same picture. But there were scientists who were looking at pictures of Neptune and studying the rings, going back through old pictures that they took of Neptune using Hubble. And there was a scientist who noticed that, hey, there's something in one or more of these pictures, and wow, there's a planet. It has a name. It's now called Hippocamp. It's named after the hippocampus, which is a mythological creature depicted as having the upper body of a horse with the lower body of a fish. And you're probably thinking to yourself, why in the world would you name a moon of a planet after that? Well, Neptune is the Roman sea god, so the Roman god of the sea. Neptune's chariot, his sea chariot, is pulled by hippocampi, upper body horse, lower body fish. Makes sense. You would have some sort of a fish-like thing driving your sea chariot. So when they were looking through these pictures, that's when they found the moon. They weren't looking for the moon. They happened upon it. That happens in science a lot. You're looking for something and you end up finding something else. But even though the Voyager 2 spacecraft flew past Neptune, it missed seeing this moon. So again, so even older pictures, or going back and looking at pictures that had already been taken, you might find things that you weren't expecting. So that is definitely an important concept in science. The thing that Hubble has seen better than anything is the entire life cycle of various types of stars. Stars form, they live out their lives, they end. How they live out their lives and end depends on how they form. And while we can't see this process from start to finish with one star, like from beginning to end, this is way too long for a human lifetime. Stars last at minimum millions of years, and at most billions, tens of billions, hundreds of billions of years. So there's no way we could ever see this whole process from start to finish with one star. So what we do is we look at lots and lots and lots of different places all over the sky, piece together the whole lifetime of stars. How they form is they all start off the same way, in giant groups, and they all form in big clouds of gas and dust. This picture you've probably seen. This is a legendary Hubble image. It was the first one that really captured the public's imagination. This is in a place called the Eagle Nebula. Now, the word nebula in Latin means cloud. When we first started pointing our telescopes at things in space, so over the last few hundred years, we would find fuzzy things. Stars are pinpoints. Other stuff is fuzzy. Anything that was fuzzy, they gave it the name nebula. So this was called the Eagle Nebula. By the way, if you're trying to find an eagle in this shape, don't. It doesn't look like an eagle. But what you've got here is a giant cloud of gas and dust. The gas is mostly hydrogen. The dust, think of it as like smoke particle sized stuff, bits of rock and metal in space. Well, we can do better than this. Hubble revisited this image 20 years later, and this is the same object with Hubble's newer camera, and you can see much more detail, right? It's a bigger image, has a lot more detail in it, but this isn't the entire story. One thing that Hubble can do is it can see light that your eyes can't see. It sees light that your eyes can see. We call that visible light. When you look around the room, you're in a room right now that probably has a light on. Light shines out, reflects off the walls. You can, to your eyes, you can see the wall. It's all because you have a source of light in the room. Things in space make light. We call those things stars. And different objects give off different types of light. And there's some light that you can see, and there's a lot of light that you can't see. One form of light that you can't see is called ultraviolet. One form of ultraviolet gives you a sunburn. A different form of ultraviolet gives you a suntan. There's another type of light that your eyes can't see called infrared. Infrared, you may know a little bit of infrared as heat. You can feel it. Your skin can detect it, but you can't see it. Hubble can detect it. So what happens when we take a look at an object like this, but we use Hubble's ability to gather a little bit of infrared light? What do we see this object looking like? It looks like this. And I'm going to toggle back and forth. These two pictures are lined up. What's astonishing is you don't even realize how much dust is blocking the view of the stars. The dust is opaque. It blocks visible light. It transmits, it allows infrared light to pass through. So you can see the light from stars that are buried in the dust. So you don't even realize how much dust is out here at the edges too. It just kind of looks like, oh, there's some stars. Well, there's actually stars embedded in that dust as well. So thousands and thousands and thousands of stars. But we see stars forming in giant groups. They form in big clouds of gas and dust. Here's a group that formed in a big cloud, thousands of stars in this one as well. And the light and heat from the stars is kind of pushed away the dust a little bit. This dust and stuff used to surround these stars, and the stars' light and heat has pushed it all away. These stars are only about 2 million years old. As far as stars go, that is really young. Here's another one. So again, thousands of stars in each of these pictures, and these stars formed in big giant groups. Our sun likely formed in a big giant group, definitely in a big cloud of gas and dust. Well, we form stars, and then sometimes, a lot of times, planets can form around those stars. So let's take a look at another cloudy thing in space, nebula, fuzzy thing. This is called the Orion Nebula. It's the fuzzy thing in the direction of the constellation Orion. The pink that you see in here is glowing hydrogen. The dark stuff is dust. And what has happened is the stars have formed within this gas cloud, and the light and heat from the stars has kind of pushed the dust away. What you're seeing, this whole thing here, it's not totally obvious. It's kind of a bowl shape. The opening of the bowl is facing us. The back curved part of the bowl is here in the back, and there's a lot of stars that are embedded in the interior part of the bowl. Well, let's take a close-up look at some of these stars. And when we do that, we see some of them have dark dust around them. You can kind of see the star a bit, right? But that dark stuff is around all these individual stars. And that dust is the type of environment where we have planets that form. What happens is this dust starts to stick together. Sometimes it sticks together to form small planets. Sometimes they form bigger planets. And we can see the very start of solar systems around these stars. They haven't formed planets yet. There's probably no planets within this dusty stuff around these stars. But maybe in a few million years, who knows? Maybe some of these stars will have planets around them. And we can see the very beginnings of that in the Orion Nebula. All right, planets form. Sometimes, occasionally, we can take pictures of these planets. Now, you're not going to get a picture like you think of, oh, here's a picture of planet Earth where you can see continents and mountains and volcanoes and lakes and rivers and all that. You're not going to see that. They're still just going to be dots. But this is a picture where my arrow is. It's a picture of a planet around another star. And how many planets have been found around other stars? Over 4,500 of them. That's one of them right there. And Hubble can take a picture of a few of these stars. If they're far enough away from the star to kind of get out of the glare a little bit, we can take a picture of some of these things. So that is a handful of planets that we're able to take direct pictures of. Hubble is fantastic for studying not only planets, but if some of these planets have air, we can detect that there's air around some of these planets. Not only that, we can figure out for some of the planets the color of the planet, if it has air. If so, maybe we can also figure out what the air is made of. We've been able to do that for a few of the planets. Like this planet right here. This is an artist's rendition. This is not a picture, but this planet is about the same color as new asphalt road. Next time you see a newly paved asphalt bit of pavement, look at how dark black the color is. That's the same color as this planet right here. I'm not saying it's covered in asphalt. It's probably not covered in asphalt, but it's the color of new asphalt. We can tell what the temperatures are of some of these planets. The temperature on this one is over 4,600 degrees Fahrenheit. The night side of this planet is a much more balmy 2,200 degrees. Just because we can find them and we can learn about them doesn't mean we actually want to go to them. So this is the case of that. Way too hot for anything to be living on this planet. But think of this, how amazing it is that we can figure all this out using Hubble and other telescopes. All right, stars live their lives and then they meet their demise. How they end up depends on how they started. Smaller stars burn cooler, last a lot longer. Hot stars are big, they burn through their fuel quickly, they don't last a long time. The example of that, there's a really good example that Hubble has studied over the decades. In 1987, astronomers were surprised in the southern hemisphere when a star exploded and could be studied from the southern hemisphere. It was close enough that telescopes on the ground could be pointed at it to study it. And this was a star explosion. It's called a supernova. And the word nova in Latin means new. We use a lot of Latin in astronomy. The word nova means new. And when long ago astronomers saw a bright light in the sky that appeared and then disappeared over the course of a few days or weeks or months, they called it, oh, new. That is something new in the sky. That is a nova, new. Later, we figured out that all these new things weren't necessarily new objects. We figured out that some of these were stars that were at the end of their lifetimes. We needed a new name for something to describe a huge star explosion. We needed something better than new, super new, as in supernova. And so that we have the name supernova to describe an exploding star. This will not happen to our sun, by the way. Our sun will never explode. But I'll show you an example of what will happen to it in a sec. But ever since 1994, we have pointed Hubble at the aftermath, the leftovers of that star explosion. I'm not going to go into the details, but I just want you to notice. Look at the picture in 1994. Look at the picture in 2016. Do they look exactly the same? No. In the one in 94, the center area is bright. The ring on the outside is dimmer. The picture in 2016, the center has dimmed out quite a bit. The ring is brighter. So you can see change over time. Every time we go back every 4 or 5 years and take pictures of this supernova aftermath, we see that system has changed. And so this has been really amazing to be able to see this. So, oh, I think I took out the picture of what's going to happen to our sun. You're probably wondering, so wait a minute, our sun's not going to explode. What's going to happen? Our sun is going to slowly, in about 3 to 5 billion years, it's going to slowly puff off its outer layers into space. So yeah, not nearly as exciting as a supernova, but it means our sun is going to last a lot longer. So that's a good thing. All right. we can use the Hubble Space Telescope to look back in time. Now, when you look out on the universe, you are always looking back in time. The time it takes for light to travel 186,000 miles is 1 second. So our moon, for example, the light that you're looking at from the moon left the moon 1.25 seconds ago. The light that you see from the sun left the sun 8 1/3 minutes ago. You're seeing the sun as it existed 8 1/3 minutes ago. You're seeing the moon as it existed 1.25 seconds ago. When you see Saturn in the night sky, you're seeing Saturn as it existed 80 minutes ago, because it took 80 minutes for the light that reflects off Saturn to get to you. So when you look at the light from the closest star to our sun, you're seeing that star as it existed 4 years ago. And as you look farther and farther away, you're looking farther and farther back in time, because it takes time for the light from those distant things to get here. And that's kind of what you're looking at here. So what they did was they had Hubble essentially stare at the same spot in the sky where we had never seen anything before. This was in the 90s. And we saw this. What you're looking at is the size of a piece of sky that, if you want to do a little experiment, find a dime, take your dime, hold it out at arm's length and look at it. Hold it up at arm's length. The size of President Roosevelt's eyeball on the dime is about the size of the piece of sky that you're looking at here. And so they stared Hubble at this spot. We had never seen anything in that area before. They wanted to see, could they collect enough light to see distant dim stuff? And they did. What you're seeing in this picture is some individual stars. All right, my arrow is pointing toward some individual stars in this picture. There's a handful of them, maybe 5 or 6, something like that. And what that means is you're looking at stars that are relatively near to our solar system. They're within our own Milky Way galaxy. We live in a solar system that has one star in it and some planets and moons and asteroids and comets. Our solar system is part of a larger collection of stars called the Milky Way galaxy. Our Milky Way galaxy has about 400 billion stars in it. If you want to look out at other galaxies, other collections of stars, you have to look past some stars in our own Milky Way. They're kind of like spots on the kitchen window. You look past the spots on the kitchen window to see the backyard beyond. So the stars in the picture are the spots on the kitchen window. Everything else that you see here is the stuff beyond. And each individual fuzzy thing in this picture, everything that you see here, except for a handful of individual stars, is another galaxy. Some of these are kind of spiral shaped, some are more round shaped, and some just kind of have no shape. But here's a nice little spiral one right here. And so what you're looking at is galaxies that are all at different distances. So each one of these, the light took time to get here. The farther away we're looking, the farther back in time we're looking at these objects right here. This view contains about 3,000 galaxies in it. This view contains about 15,000 galaxies in it. And again, individual stars here, there, a couple others here, a few more. Pretty much every other thing in this picture is a distant galaxy. And some of these you may see, if you're looking at this on a laptop or desktop, you might see some of these are decidedly red. The farther away we see something, the redder it appears. And so some of these objects in this particular picture are some of the oldest things we have ever taken a picture of. Some of the most distant objects we've ever seen. However, Hubble has limits, and the successor to the Hubble Space Telescope will build upon its amazing work. And that's called the James Webb Space Telescope. It is scheduled to launch in a little over a week at 6:20 in the morning. Fingers crossed. Now, development of the follow-on mission to Hubble started in the late 1980s. I told you that the launch date was 1990. We started working on the successor telescope before Hubble even got off the ground. This is a very early design idea for this telescope. It doesn't look like this, but it could have. And they started designing the telescope in 1996. It was supposed to launch in 2007. It is now 2021. Why the delay? Making a really big telescope is really hard. It's really expensive. Testing a really big telescope is really hard. It's really expensive. COVID has made things really hard and really expensive. So all of that has conspired to really delay this and cause it to cost a lot more than they originally thought it would. This is a full-size model of the James Webb Space Telescope. This image was taken about 15 years ago. And this is the mirror of the telescope. And you can see it's made of individual pieces. Those individual pieces are movable. And so they can adjust the shape of the mirror if it gets a little bit out of whack, which it would over time. But there you go. You've got built-in ability to correct for a flaw. So they're going to launch this with the mirrors probably a little bit out of focus. And then once they get the telescope into space and do a bunch of other stuff, they'll align these mirrors. And so they have the ability to move each of those individual mirrors. These are only a handful of the people who have helped build this telescope. And this is an artist's rendition of the James Webb Space Telescope. What this thing is going to look for is light from the earliest stars and galaxies, to study the formation of galaxies and how they evolve over time, to study the formation of stars, study the formation of planets, and study systems of planets. We'll also look at some exotic stuff, like they're going to look near black holes and stuff like that. But I showed you examples of stuff that the Hubble has done just to show you that we've been able to look to a point with Hubble. James Webb will take us to the next step and beyond, to be able to learn about these various things. Now, the telescope is going to look completely, totally at infrared light. I mentioned infrared light before. It will not look at visible light. It will only detect infrared light, because infrared light will give us even more information than we had before. Hubble can see a little bit of it. James Webb can see a lot more. These are all of the participating countries in the James Webb Space Telescope program. So all these other countries, in exchange for stuff, in exchange for people working on the program, they're going to get time on the telescope. So, these other countries have provided instruments, the rocket, all sorts of stuff to be able to then be able to have their scientists be able to get some data from the telescope and do observations with it. So it's a good partnership. This happens in astronomy and space exploration all the time. Lots of times countries do not exchange money, they exchange stuff. And so kind of like a barter system. If I give you the rocket for the telescope, will you give me X amount of time for my scientists? And yeah, that's exactly what's going on here. The telescope is going to orbit almost 1 million miles away from the Earth. It's not going to go in a big circle around the Earth. It's going to go in a big circle around the sun. But it will be able to stay at that point pretty easily. That big shield part, the big gray stuff, the big sheeting there, is how it will keep itself cool. It will point that toward the sun so that the telescope points away from the sun to keep it cool. The mirror, you can see the size of the mirror is a lot bigger than the Hubble Space Telescope mirror, but we'll be able to see some very good detail. The mirrors are covered in gold. And if you're wondering how much gold we're talking, if you scrape off all the gold off the mirrors and melt it, you will end up with a ball of gold the size of a golf ball. So all that for a golf ball size amount of gold. That's more gold than you and I will ever have, more than likely. but it's really not a lot in terms of what is on the outside of the mirrors. It's very reflective and very sturdy. And so it's a good material to use, very stable. Here you can see the assembled mirrors. You can get a sense of how this thing is going to fit into its rocket. It's all folded up. You may have been wondering, how are they going to get that thing into space? All folded up, telescope origami. Here's what the telescope looks like unfolded. It's a gorgeous telescope. I wish I could have seen it in person. But the shield to protect it from the sun is this stuff right here. So again, the mirror will go on one side of this shield. The antenna will go on the other side. And the antenna side will be the side that faces to Earth. And again, if you're wondering how this all is going to fit in the rocket, here is your telescope origami. It just fits. So it's going to launch aboard this rocket right here, which is called an Orion 5. And it's going to launch from just off the coast of South America. The European Space Agency is providing the rocket. And so that's why it's launching from there. Also, this launch pad is much closer to the equator than what we have in Florida, which is here. So much closer to the equator means you get a little bit more boost from the rotation of the Earth when this thing gets off the ground. So little extra oomph, which means you need a slight little bit less rocket fuel to get this thing into space. If you want to learn more, I'll put these links into the chat, but all of the Hubble images and literally thousands more are available on the Hubble Space Telescope website. And the James Webb Space Telescope site also has a lot of pictures and information about the mission. So why don't I grab these while I'm thinking of it? So give me just a second. And I'm going to put that in the chat. There we go. All right.